Lecture 5 covers Section 3.1.3. At the end of today's lecture, you should be able to project a moment onto a line. Now, when a three-dimensional force acts on a three-dimensional position vector, i.e. a moment arm, we are going to create a three-dimensional tendency for rotation about a point. For instance, if we have F acting on point A, which is the point of termination of a moment arm, which has a point of origination at B, we are going to create a tendency to rotate about point B. Now let us decompose these vectors into our principal components, i.e. the x, y, and z components, to determine the contribution of each to the moment in each of our principal directions. To begin, we will focus on the force in the x direction, and we see that its line of action is perpendicular to rz, the z component of our moment arm. If we use the right-hand rule, we see that we are going to create a moment about our positive y-axis. And this moment can be defined as r sub z, f sub x, in the j hat direction. Now additionally, the line of action of f of x is also perpendicular to r sub y, the y component of our moment arm. And using the right-hand rule, we see this creates a moment about our negative z-axis. And this moment can be expressed as r sub y, f sub x, k hat, quantity negative. We see that f sub x does not act on r sub x since they are parallel to one another. Now, if we look at f sub y, we see its line of action is perpendicular to r sub x, the x component of our position vector. And using our right-hand rule, we see it creates a moment about our positive z-axis. And this moment can be expressed as r sub x, f sub y, k hat. Additionally, the line of action of f sub y is perpendicular to r sub z. And once again, using the right-hand rule, we see it's going to create a moment about the negative x-axis. And this moment is going to be expressed as r sub z, f sub y, I hat, quantity negative. And once again, f sub y and r sub y do not interact since they are parallel to one another. Lastly, if we focus on f sub z, we see its line of action is perpendicular to r sub y. And using our right-hand rule, we see it creates a moment about our positive x-axis. And this is quantified as r sub y, f sub z, I hat. Lastly, the line of action of f sub z is also perpendicular to r sub x. And using the right-hand rule, we see we create a moment about the negative y-axis. And this moment is expressed as r sub x, f sub z, j hat, quantity negative. And f sub z and r sub z do not interact since they are parallel. Now if we bring together all our terms, and grouping these based upon direction, we can say our moment about point B is equal to quantity r sub y, f sub z, minus r sub z, f sub y, I hat, plus the quantity r sub z, f sub x, minus r sub x, f sub z, j hat, plus r sub x, f sub y, minus r sub y, f sub x, k hat. Now we note this would yield the same product as executing the cross product of r and f, which would be the quantity r sub y, f sub z, minus r sub z, f sub y, I hat, minus the quantity r sub x, f sub z, minus r sub z, f sub x, j hat, plus the quantity r sub x, f sub y, minus r sub y, f sub x, k hat. Now what's nice about this formulation is we can call the terms within the parentheses the principal scalar components of our moment. For instance, r sub y, f sub z, minus r sub z, f sub y, this could be denoted as m sub x, the scalar component of our moment in the x direction. Thus we can express our moment about B in terms of our scalar components, multiplied by our unit vectors to indicate direction, or we can break down m sub z into our x, y, and z components. That is, we'd have m sub x with a vector hat, plus m sub y with a vector hat, plus m sub z with a vector hat. In example 1, let us consider the application of a force on a point. That is, we have F acting on A. The force has a magnitude of 100 newtons, and it's described by the unit vector 0, square root 2.000 divided by 2.00, and the square root of 2.000 divided by 2.00. Now point A has coordinates of 10.0, 4.00, and 4.00 meters. We want to determine the moment of force about point O. The moment of force about point O is simply found via our cross product. That is, our moment about O is going to be equal to R cross F, which we're going to take the determinant of a 3 by 3. Our first row is our unit vectors, I hat, j hat, k hat. Our second row is our position vector, going from O to A, of 10.0 meters, 4.00 meters, and 4.00 meters. F we determined by multiplying our force through our unit vector, describing F, which is 0, 70.7 newtons, and 70.7 newtons. When we determine our moment in the x direction, we'd have 70.7 newtons times 4.00 meters minus 70.7 newtons times 4.00 meters. And that term is going to go to 0. In our y direction, we'd have the negative of the quantity, 70.7 newtons times 10.0 meters minus 0 newtons times 4.00 meters. Thus, we're going to be left with minus 707 newton meters in our y direction. In the z direction, we're going to have 70.7 newtons times 10.0 meters minus 0 newtons times 4.00 meters. Thus, we'll be left with 707 newton meters in our z direction. Therefore, our moment of force about point O is expressed as 0, minus 707, 707 newton meters.